All right, hello everyone. Welcome back. In today's video, we're going to be working an AP problem. That's an accumulation of change problem. Um, let's see. So let's just have you take a minute to read through the setup here. We're going to be working the same problem on both of the pages today. I got part A and part B on the front page, part B, part D, part C, part D on the second page. Okay, so as I'm reading through this, I see a couple things. I see two functions, each of which are rate functions. Okay, so they are like something else's first derivative. If I want to find an amount, I'm going to probably have to integrate. Additionally, I see an initial condition. So if I ever have to find like a total amount, I need to make sure I'm incorporating that. Our first question is, how much sand will the tide remove from the beach during this 6-hour period? Indicate units of measure. So I'm just looking for the equation that represents how much it removes, which is our top one here. Let's see, and it says over this 6-hour period. So I want to know how much this rate function accumulates between the first and the 6th hour. So I'm going to integrate it. Again, just like last time, this would be a calculator problem. Usually it's kind of a giveaway. They'll give you functions that'd be really goofy to integrate on your own. Numerical integration, hit your limits. I know you know how to push buttons. So I would say push them yourself. Make sure this is what you get out. Something else we got to think about, the units of measure. Let's see. Both rates are cubic yards per hour. But then when we're integrating, remember, that would get rid of a factor of time. So I think our answer here is just going to be in cubic yards. In part B, we are tasked with writing an expression. So we're coming up with a new equation that for the total number of cubic yards of sand on the beach at a certain time. Okay, well, we know the amount on the beach starts with 2,500. So you could either put that in the front or you could put that at the end. And then we know we'd have to factor in how much gets added from the pumping station and how much gets removed from the tide. Here's the tricky part. And this is an annoying thing, but remember how we said you can't use the same variable in two places. Each of these functions are defined in terms of time, but if we're going to integrate them, we can't integrate from 0 to t of the input function minus integral from 0 to t of the output function. It's using the same variable in both of these places that is improper. So what we're going to do is just change one of them. And I want you to change the input variable. So I guess we have to change the dt as well. You can rename it whatever you want. You can say it's s of x dx, r of x dx. But because we want our answer in terms of time, then I have to leave time in the upper limits here. But you can replace the variable in the function with any dummy variable you want. It doesn't matter. Because literally you would just be replacing, you'd say, okay, if s of t is that, then s of x would be 15x over 1 plus 3x. You don't even have to write that. It's just understood. That would be the case. Then you integrate it from 0 to t. Now you have t as your upper limit. So it's okay. So again, this was our initial amount. This is how much gets added. This would be the accumulation of the change of the amount that gets added. And then this would be the accumulation of the amount that gets removed. That's why we're subtracting it. Let's look at the next page. So again, same setup here. The new stuff starts here with part C. Find the rate at which the total amount of sand on the beach is changing at time 4. Okay, well, we came up with that amount. Remember, y of t was the amount on the sand of sand on the beach. So if we're trying to figure the rate at which that's changing, that would be the derivative of y prime. Or I'm sorry, be the derivative of y. So first off, I'm just going to recopy our y here, plus integral 0 to t. What was it? S, R. S of x, and then from 0 to t. So what do we need here? We need the derivative. We need y prime because it says find the rate of change of the total amount. Well, derive this whole thing from left to right with respect to t. The derivative of any constant is 0, so it's gone. Then, fundamental theorem of calculus time, integrating would kind of bring this function up a level, but then deriving would bring it back down, and we're just going to have this guy left behind. We don't even have to worry about the chain rule because it's just t. It's not t squared. It's not 2t or anything. So I think we'd have r of t minus. Same thing over here. You'd integrate it, but then you'd derive it back down a level, and you'd just have the upper limit here. You're missing the 0 because, okay. If this bugs you, I don't know. If this doesn't bug you, fast forward 30, 60 seconds. I don't know. If this does bug you, again, remember, what would we do? We would find the antiderivative of r. I don't know, super mega capital R, since it's already capital. We'd plug in t. We'd plug in 0, super mega capital R of 0. Then we would derive this. Well, this one here would be a constant. That's why it's gone. Then the derivative of super mega capital R would go back to regular capital R. Same thing with the s. Okay. And then it specifically said at time 4. So we would need y prime at 4, which is just r of 4 minus s of 4, which, get out your calculator, plug 4 into each of these, subtract them, you should get negative 1.909. Don't forget your units. Because we're working with just the rate functions, we'd be back to cubic yards per hour. You might think to yourself, Mr. Doolin, why did I have to derive the amount? I already knew the rates individually. Why did I have to derive the amount? You don't. You don't. You could have just jumped straight to this, and that would totally be fine, if that makes sense to you. Our last sub-question is, for the time interval 0 to 6, at what time is the amount of sand a minimum? Ah, our favorite. We loved these problems back in Unit 3, didn't we? What is the minimum value? Justify your answers. Okay, well, let's see. How do we normally find extreme values? I know it's been a while, so basically we need the minimum value of y of t, right? What would we do? We would derive it, we would set it equal to 0, and then we would solve. We would also look for where it's undefined as well. This will find our critical points. These are going to find the only places where the function could be at a max or at a min. Great news. We already know the derivative. It's r of t minus s of t. And we know this either has to be 0, again, or undefined. You can solve this however you want. You can graph it like this and find the t-intercept. Or you could slide it over. You could graph r of t and s of t and then find the intersection point. Exact same thing. Whatever your preference is. And that'll get you the critical value, the time at which the derivative is 0 is 5.118 hours. So again, your favorite method to do that, it doesn't matter. But don't forget, extreme values can also happen at endpoints. And I know it's been a couple months since we did a problem like this. So here's what we liked to do back in the day. We would make a little chart. You don't have to do this. You do it however you want. We'd have the time. We'd have the amount of sand or whatever it is. I've got my initial value 0. I've got my critical point, and I've got my final value for time. And then we need to evaluate what is the amount of sand at each of these points. We were given the initial condition. We were told in the setup, right over here at time 0, there's 2,500 cubic yards of sand. Okay. Now I just need to evaluate my y of t for the other two. I need to do it for 5.118 and 6. No better time than the present to use your calculator again. What's going to be different than this? You're just going to be plugging in 6 or 5.118. So I would say, like in my calculator, I would do 2,500 plus the integral from 0 to 5.118 up. And you can actually condense those two integrals together because they're just subtracted, right? So you could say, I'm just going to say r of, again, x, I guess, since I probably shouldn't use the same variable twice, minus s of x dx. You punch this in your calculator. Actually type out the whole function. Don't type r parentheses x. And you will find the amount at that time would be 2492.369. Punch it in again with 6 as your upper limit. See what the answer is this time. 2493.277. Double check the question. What was it? What was the minimum value? The minimum value is this one. So let's see, 2492.369 yards cubed of sand when t equals 5.118 hours. We've justified our work by, 1, deriving, just checking for 0. We use our calculator to find the time, but that's okay because then we also used calculus to find the amounts everywhere. And yeah, that's it. To be honest with you, we usually see an accumulation of change free response question about every other year on the AP exam. So this would be a good one to make sure we master because it comes up, this skill, this style of problem comes up all the time. So see you guys next time.